I'm Peng Liu, a researcher at SINTEF in Norway. I'm delighted to be a part of this urban home ventilation webinar. So today I'm going to talk about understanding moisture recovery in heat and energy recovery ventilation as the basis for new market solutions. The presentation will specifically focus on how moisture could be regenerated intentionally and unintentionally inside heat and energy recovery units. We begin with the three questions. The first one is, when does moisture recovery occur? And the second question is, what amount of the moisture is recovered? And the last one is, moisture recovery needed. In this presentation, we will focus on the first two questions. I will leave the last one to you. Hopefully, you can also pick up some hints for answering the last one after we've been through the first two questions. So actually, it's already been somehow answered in Svella's talk, I think. Before we dive into answering the questions, to avoid misleading you to a wrong destination, I would put things on the conditions we are in. So it could be what's about or not about today's presentation. It's about cold period. In cold or temperate climates, we are looking at the moisture recovery from the warm and humid exhaust air side to the cold and dry supply air side. So it's not about hot and humid climates where the moisture transfer is reversed. It's about air-to-air heat and energy recovery units, which are commonly applied for residential buildings, mainly two types, regenerators and recuperators. We will look into these two types of heat and energy recoveries later in this presentation. It may be not applied to other types of heat recovery, like exhaust air, heat pump, heat pipes, or run-around heat recovery. It's about balanced mechanical ventilation for residential buildings. It's not about natural ventilation. The residential building is well insulated and airtight. The poorly insulated and bad airtight building will reduce the effect of heat and moisture recovery. Now let's back to the questions. When and what amount of moisture are recovered? The answer could be intuitively reflect with this relationship. The moisture recovery rate is a product of indoor moisture excess and the moisture recovery efficiency. The internal moisture excess represents the maximum moisture recovery potential. When it's multiplied by the actual recovery ratio, then yields moisture recovery rate. So we will investigate each term to see what it means and how to determine them. First term, internal moisture excess. The internal moisture excess is defined as the difference of the moisture ratios between indoor and outdoor air. It's the maximum moisture recovery potential. So as this difference between indoor and outdoors is apparently influenced by the internal moisture profiles and weather conditions of the building location. For the internal moisture profiles, different activities generate moisture indoors. It could be from respiratory activities of occupants, pets, and water vapor from the indoor plants. The moisture generation activities such as bathing or showering, cooking, dishwashing, laundry, drying, and cleaning. The indoor moisture profiles are also influenced by the ventilation, which include infiltration and ventilation air from heat recovery units. The moisture recovery will in turn influence the indoor moisture profile. So the moisture recovery and the indoor moisture profiles affects each other. They are coupled. The internal moisture excess for cold period have been considerably studied in the literature. The figure on the left shows the weekly average of the moisture excess of 101 timber-framed single-family buildings as a function of a weekly average outdoor air temperature. And the dotted line represents the moisture excess curve on the higher 10% critical level. The figure on the right shows that the internal moisture excess tends to be generally considered as relative constant in the house during the colder part of the heating season until 5 degrees Celsius, where the internal moisture excess decreased linearly down to a constant at 15 degrees Celsius and a higher temperature. Then we move forward to the second term in the relationship of a calculated moisture recovery amount. Moisture recovery efficiency. The moisture recovery efficiency is the ratio of the recovered moisture in the air supplied to the house to the moisture that is expelled in the exhaust air. Different types of heat recovery units can or cannot recover moisture. So the moisture recovery efficiency is varying with the different heat recovery characteristics. It's necessary to differ different types of heat and energy recoveries. In this presentation, we focus on two types of heat recovery or energy recovery, namely regenerators and recuperators, which are commonly applied in the residential buildings. For regenerators, the heat transfer between exhaust and supply air streams through a rotating core that picks up and stores heat from the hot stream to a cold stream. Regenerator can be further categorized as heat wheel, which is non-desiccant, and enthalpy wheel, which is also called desiccant wheel, if the non-desiccant surface is coated with a desiccant material. The enthalpy wheel allows increased moisture transfer. For recuperators, it's a static heat exchanger without moving part compared to the rotary wheel. The heat is transferred from the hot stream to the cold stream directly through the separating plates. The plates is often metallic material or impermeable plastic. When the impermeable plates are replaced by the permeable membranes, which are able to transfer both heat and moisture, then it's called membrane energy exchanger. Now let's first look at the moisture transfer in the rotary and the enthalpy wheels. In a heat wheel, the water vapor in warm and humid airstream tends to be cooled down in the airflow direction with the temperature loss due to the heat transfer. So the water vapor starts to condense on the surface when the temperature is lower than the dew point. The condensation water is rotated to the cold and dry air side with the rotation of the surface. So in this side, the condensation water adhere to the surface, start to evaporate to the cold and dry air. So in this way, the moisture from the exhaust side is transferred to the supply side. If we look at this process in the stoichiometric chart, on the right side of the stoichiometric chart, the extract air relativity is 30% at 20 degrees Celsius, represented by the red point 1 here. And the outdoor temperature is minus 15, represented by the blue point 1. In the graph on the left, right-hand side, the extract air red point is first cooled down to the dew point at the red point 2 and start to condensate. Form wet condensation area in the heat wheel and exhaust to the outdoor air through the connected duct at red point 3 during this half period of the rotation. So for the next half of the rotation, the cold, dry outdoor air enter the wheel at blue point 1, and the condensation start to evaporate to the air. And from blue point 2, the condensation is completely evaporated to the supply air. We find how the supply air is heated and humidified in the stoichiometric chart from this blue line from 1 to 3. And if there's no moist transfer through the condensation and evaporation, the outdoor air will be heated from point 1 to 3 prime in green, so which is drier than this blue point 3. And the difference between 3 and 3 prime in green is actually the recovered moisture in a heat wheel through condensation and evaporation. If the outdoor relativity becomes 60, the effect of the moisture recovery from the condensing heat wheel On increasing the indoor air relative humidity and the supply air absolute and the relative humidity become more significant. So this is the recovered moisture. For Enthalpy, a desiccant material is coated on the metallic surface. So the water is absorbed to the desiccant coating. Then it evaporates to another side with the wheel rotation. The moisture is released to the cold and dry air streams and add humidity to the supply air. In this process, the moisture transferred is through absorption and desorption, not necessarily through condensation and evaporation, as in the non-desiccant heat wheel. So the moisture transfer process for Enthalpy wheel is quite linear in the stoichiometric chart. You also find that the recovery moisture for different extract air relative humidity 30% and 6%. For the non-desiccant heat wheel, in practice, the metallic surface characteristics in a heat wheel may change over time during the oxidation or falling. The surface may become partially hygroscopic, desiccant-like, which means it's likely to absorb and desorb moisture as in Enthalpy wheel. However, its ability of absorption and desorption is not as strong as Enthalpy wheel, and the condensation and evaporation may also occur at the same time. So this makes the moisture process become a combination of a heat wheel and Enthalpy wheel. And then in the stoichiometric chart, it combines the mentioned two processes. The moisture transfer in the heat wheel due to oxidate or fault surface is less known and studied. Now we can move to the moisture transfer in plate and the membrane energy exchanger. In the plate exchanger, the warm and the humid extract air is cooled down, and it starts to condense along the flow direction with the heat recovery. Because the plate is impermeable to water vapor, the moisture can't transfer to the other sides. So the moisture in supply air sides is unchanged. For the plate exchanger, a drainage duct to collect the condensation water is usually needed for cold climates. In stoichiometric chart, if the extract air relative humidity is 30% and outdoor temperature is not too low, then the plate exchanger is totally dry. When extract air relative humidity is 60 on the right-hand side, in the exhaust air side, there is a condensation forming. In both cases, the moisture will not transfer to the supply side, so the humidity ratio in supply air side from this blue point 1 to 3 are unchanged. So no moisture is recovered for the plate heat exchanger. But when the plate is changed to membrane, which is permeable to water vapor, then the moisture from the exhaust air side transfers through the membrane to the supply air side with the humidity gradients as the driving force. Moist transfer process of the membrane exchanger in the stoichiometric chart is identical with in Enthalpy heat wheel. Compared to the rotary Enthalpy wheel, the membrane energy exchanger is static, so the need of the maintenance is low. At the same time, membrane energy exchanger can also reduce or avoid carryover and the leakage risk compared to the rotary wheels. So better indoor air quality is expected with using membrane exchanger. As the moisture is in exhaust side recovered to the supply sides, the condensation and the frosting risk inside the exchanger are also low for membrane energy exchanger. Membrane energy exchanger prototypes have been constructed at our laboratory. So the figure on the left-hand side shows the heat and moisture recovery efficiency for counterflow membrane exchanger around 90 and 80% respectively. The figure in the middle shows that the frost formation in the plate heat exchanger and membrane energy exchanger with the same heat recovery efficiency in two exchangers. The frost formation and frost amount is indicated by the pressure drop through the exhaust sides for both exchangers. HRV is plate heat exchanger and the ERV is the membrane energy exchanger here. The pressure drop in the plate heat exchanger grows much higher over time than membrane energy exchanger, which means less frost forming in the membrane energy exchanger than in plate heat exchanger. The figure on the right is the picture of the frost at the outlet of the exchanger. How does the moisture recovery in membrane energy exchanger influence the indoor moisture profile compared to use plate exchanger? This has been simulated for a single-family house in Oslo with 2 adults and 1 child present in a building. The moisture production schedule is applied. The heat recovery efficiency for membrane and the plate exchanger are the same, 80%. The membrane has 60% of the moisture efficiency, while there's no moisture recovery in plate heat exchanger. So the red curve represents the hourly indoor relative humidity in living room over a year with using membrane energy exchanger. The black one is for using plate heat exchanger. So due to the moisture recovery in membrane, the indoor moisture level with using membrane exchanger is generally higher than using plate exchanger. Membrane exchanger increases the indoor humidity by 7% on average compared to using plate exchanger in this case. The shaded area is the desirable indoor humidity range in this case from 30 to 60%. If the plate exchanger is used, there's 3,876 hours, and that's 44% of the time of the year is within this 30 to 60% range for the indoor humidity. While using membrane energy exchanger, the number becomes 5,695 hours, and that's 65% of the time of the year is within this range. So membrane energy exchanger is actually increased 21% of the time during the year for indoor relative humidity in this preferred indoor relative humidity range. To wrap up what we have talked about, we attempted to answer first 2 of these 3 questions, and we talk about the first 2 questions by breaking down the moisture recovery to the internal moisture excess and the moisture recovery efficiency for different types of heat and energy recoveries. The membrane energy exchanger is the relatively novel solution for cold climates, and its impacts on the potentially benefiting indoor humidity level are presented. So hopefully now you also get some inspirations for the last question. Is moisture recovery needed? And I will leave this to you. And this is the reference we used in this presentation. And also thanks go to Hans Martin at NTNU, Annelie, Daniel at Flexit, Maria at NTNU and SINTEF for preparation of these results and slides. It has been supported by Energy Bolig, Diffuse Me Now, and Healthy Energy Efficient Urban Home Ventilation Projects.